Great. Yeah, thank you very much for the invitation. So now you can get the doubloon from the masts that has been put there by Captain Ahab. Anyways, yeah, thank you very much for the invitation. It's been a real pleasure to be here. I've learned a lot, and actually also a lot of what's coming now in my talk has already been presented also in the talks of Alexander and Esther. So it's going to be a lot of just recapping, but I hope to maybe bring a little bit of a different perspective to this. Okay, so first, let me quickly introduce myself. As Georg said, I'm Johannes Margraf. I'm now, since 2 years, at the University of Bayreuth. So this is here in the northeastern corner of Bavaria. And before this, I was in Berlin at the Fritz Haber Institute. So my group is still slightly delocalized because some people are finishing up. But yeah, now we're mostly in Bayreuth. It's a very nice place. Come visit us. The train connection is a bit faulty now, but we will make it happen. So if you want to come visit, if I have to pick you up by car, I will. So just let me know. Anyways, and this is my group, and I just quickly want to already shout out some people whose work I'm mainly going to present. So this is Martin Wondrak. He's been working on long-range interactions for machine learning models, which I think is still an important open question that we have to tackle. So that's going to be towards the end of the talk. And then Connie and Niels have been working with foundation models, kind of developing them and applying them for different things. And I think we've also learned a lot now about these models and what they can and can't do, which I want to share with you. Okay. So let me start super basically. I mean, this is all very trivial from you, but I just want to get us on the same page here. So when we talk about machine learning, basically we're talking about having some samples of data, y and x, and then we want to learn the function that connects these y's and x's to each other, right? So in the simplest case, x is just one-dimensional and y is a scalar. And then if we have here two samples, we could, of course, fit any number of functions to this data. And so what you do in machine learning is you pick a certain family of functions, you fit them to this data. And as more data becomes available, because you've chosen a sort of flexible algorithm, right? You did not just use linear regression of x against y, but you chose a flexible algorithm. So this allows you to kind of adapt to new data. And the important thing is that as you see, there's a new data, these red points that are coming in, will increasingly kind of fall on the blue line, right? Which means that your model not just learns to kind of fit the data you have, the training data, but it becomes predictive. And this predictive error very systematically decreases as we increase the training set size, right? And that's nice because this gives us a handle on, without making any assumptions, without kind of starting from scratch, we basically just need to add more data to improve, by and large, right? And that's what is very attractive about these methods, and that's why they are used in so many places, right? Because they have a very straightforward recipe for how to improve them to the desired level of accuracy. So that's nice. A learning algorithm compared to just a normal fitting with a fixed functional form improves with more data. Doing a linear regression on the first two data points would give me the same agreement with the data, but it would not have this property of improving with more data. And of course, then the caveat here is that this fit is, of course, very nice and it's predictive within the domain, right? So I'm just sampling here between 0 and 10. All bets are off if we go to 11 or -5 here. And I think this is an important point, right? And this is why generally we say that we are interpolating, although strictly speaking, this is not really true in high-dimensional space because interpolation in high-dimensional space is very difficult. And so, but this is really the critical question always, right? I think also in the previous talk we heard about these trust issues that we all, I think, have with these machine learning potentials, right? It's very nice, but when are we finished? When are we done training? This is always an open question. And the reason it's an open question is that it's always possible that we end up in some new domain, especially if we're doing exploration, if we're doing predictive science. And then we'd want these models to still work. And I think this is something that we've been worrying about a lot. I think Esther also showed very nicely that uncertainty estimation can be a super nice tool in that direction. Okay, good. So this is a toy system, and in reality, and this is just something I took from literature, these learning curves look like this. So this is a kind of, still you could say a toy example. So this is QM9. It's a big data set of small organic molecules for which the atomization energies have been computed. And you can see here that sort of these different types of algorithms. In this case, it's mostly different types of descriptors, different ways of kind of encoding the structure. They all have this learning property, right? As we add more training examples on a log scale, we get kind of a linear improvement in terms of the mean absolute error, also on the log scale. So this is this learning behavior. But this also shows that it's not just the adding more training data that is key. The other thing we can do, so there's a lot to gain, even at a fixed training set size, by changing our algorithm, changing our descriptors, right? So if we make our methods better with a fixed training set size, we can also increase their accuracy. And a big region of interest, say, in these general learning curves that I've mostly been working on is the small data regime, right? And that's because, as I just discussed in the coffee break with Georg, I've been somewhat of a skeptic of the big data regime, right? And I've now been converted to some extent. But my bias going into this was always that, I mean, the reason I want to do machine learning is because for the kinds of simulations I want to do, DFT is expensive, or quantum chemistry is expensive. And if I need 100,000 DFT calculations to get my model going, right, that's kind of what I would call the big data regime here, then that's a big upfront cost, right, that I was trying to avoid in the first place. So for a lot of my simulations, if I do some geometry optimization, I don't want to do 100,000 training calculations to do like 20 steps of geometry optimization. That's obviously not efficient. So that's why we were focusing a lot on the small data regime. We were using kernel methods, which have nice built-in uncertainty estimates, and they are very fast to train, as for example also Georg knows from the VASP MLFF, which also uses these kinds of techniques, right? So they have a lot going for them there. And at the same time, because I was kind of a kernel methods guy, the big data regime was also, from a technical perspective, unattractive for me, right? Because these kinds of algorithms, they have fast training times for small training sets. But as your training sets become larger and larger, the memory demand, also the CPU time for training them becomes very big. So they become unattractive, right? But in this region, the graph neural networks have now emerged as really the state-of-the-art methods. And they can handle these things. And of course, as I mentioned, the key thing then is if you're going to do 100,000 or 1 million or even more, hundreds of millions now in some data sets, DFT single point calculations, that better be useful for more than just one single simulation, right? So then you need to be transferable. And this was always for me the big question. Okay, we can do it technically. We can go to large data sets. We can generate large data sets using workflow tools. But are we ever going to be transferable in a way that this upfront invest is actually worth it? And I think it is now, but I didn't before, and I want to kind of explain that trajectory a bit and my thoughts on that. All right. So just to get us started, what is kind of the typical small data regime things that we and many other people have been doing? Well, so the first thing is you take kind of a representation of the chemical structure, because what we want to do is we want to use this as the input, the full geometry of a system, and we want to predict the stuff that would come out of a DFT calculation. So that's energies and forces, but it can also be other things like, if it's a molecule, an orbital energy, or a dipole moment, or any kind of property you get out of a DFT calculation. And of course, you want to use here the full geometric information, right? So this is not the realm of sort of more chemoinformatics fingerprint type methods, because we are looking for the precise information for a certain configuration of the atoms, and also we want the response of our target property if we change the geometry. So we need the full geometric information. We want to be efficient, obviously. The whole point is to be more efficient than DFT, and significantly more efficient. And then there's some, as it has emerged, some symmetry properties you want. So you want a unique descriptor. You don't want two different atomic environments or two different structures to map to the same descriptor, because that would make learning difficult, right? Or impossible, actually. And you want to probably build in some symmetries and invariances that your target property has. So this is a very important point that has kind of emerged in the community, right? If your energy is rotationally invariant, or if it's translation invariant, or permutational invariant when you mix or when you switch two identical atoms, then you want, of course, your machine learning model to a priori also fulfill these symmetries. And the final thing that I'm a big fan of, and also I think the rest of the field is a big fan of, you really want to be size extensive, because your DFT calculations are not linear scaling in most cases, meaning that it's very, or comparatively cheap for you to generate training data on small systems, as Esther has also shown. But the DFT on the large system becomes prohibitive very quickly. And so if you want to run machine learning potentials on large systems, it's very nice if you can train them on small ones, right? And all of this then leads to this general idea that is kind of, I think, going back to Jörg Behler and Michele Pavinello with the atom-centered symmetry functions, that you want these atomic environment-based descriptors. And there's been now a range of different models here. SOAP, which is what we've been using a lot. FCHL, ACE, which is, I think, the most recent, most advanced of these kinds of descriptors. And they all have this basic idea that you take each atom in your system, you draw a sphere around it, and you try to describe the atomic environment. And then whatever you're predicting, if it's an atomic property, like a NMR chemical shift, let's say, you can directly get that from this descriptor. And if it's a global property, like a dipole moment or a total energy, then you need to somehow aggregate these local environment informations to the global property, right? But that gives you the size extensivity. It also gives you permutational invariance and all of these nice features, right? So this is a very powerful idea. And one thing that we found this very useful for in our applications, so especially in Berlin, I was working a lot with catalysis, heterogeneous catalysis. And so if you're looking at a somewhat more complicated process, something like ethanol synthesis, where you have a bunch of, small but not trivial organic molecules that can kind of be created on the path in the reaction network of these, then one problem you have is the thing you need to describe the microkinetics of this system is the absorption energy of each intermediate. But this is not well defined because the intermediate has conformational freedom and also the surface has different absorption sites, right? So in a complex reaction network where you have many of these different intermediates and a non-trivial surface like maybe rhodium-211, which is the stepped type surface, you have a kind of complex global optimization problem for every single species in your reaction network. So getting a fast approach to determine these Azimut geometries was a really important thing for us. And this was really, I think, a nice success story where these kinds of active learning methods using gap potential in this case and the minima hopping algorithm as a global search method worked very nicely. So you can see this here. This is sort of the same thing as this toy example I showed you before. You can see here the root mean square error on the forces of our model against the global search iteration. And by adding very few, I think in this case it was just 2 single point DFT calculations at each iteration. So you end up with something like 30, 40 DFT calculations that you have to do for one Azimut on one surface. You get a nice converged model. And what I really always appreciate about this active learning thing, and I think this is also something we saw in Esther's talk, is that it allows you to train the model on configurations that you would not think are useful or good, right? So this is, of course, the initial model is very bad, has very bad chemistry. It kind of does overlapping atoms. It does unreasonable valence angles and all these things. But that information can be quite useful for our model to learn to avoid these things, right? And if you show him a few of these configurations, you get a very robust model that you can now use. And if you still have these trust issues that we all have, you can even then do final DFT relaxation on the output of your model and have a pretty high confidence that you've now found a good configuration for that system. And because it's so cheap, you can do this on a bigger scale. So you can do kind of these parallel, I think these are like 40 parallel simulations. And you can kind of then follow them all. So each of these gray lines is one of these global optimizations. They then share a pool for the fitting of the potential. And you can see that several of these gray lines rediscover essentially what we think is the global minimum here. So this gives you some confidence that you're actually found the global minimum, right? If you have independent runs and they rediscover the same global minimum several times, that is one way of having some confidence that it's actually the global minimum. And at the same time, it also gives you sort of a landscape of the different configurations that are out there, right? It might not even be just the global minimum that is relevant, especially if you're then also looking for transition states or things like this, then the global minimum is very often not a good starting point. But anyways, so that was kind of that story. We were very happy with these kinds of approaches. We still use them sometimes. But the downside here, in a way, is that this is very like single-use type, right? It's not a very sustainable way of doing machine learning, because we fit the machine learning potential for this very purpose of just doing the global optimization of this one atzibit on this one surface. So if you have a bunch of atzibits and a bunch of surface, we do a single-use potential for each of them, and then we throw them away afterwards, right? The only thing we care about is sort of the output, the geometries we get, but not the machine learning potential itself. So if we do this a lot, you could argue that we end up being wasteful, right? We end up in the regime of hundreds of thousands of DFT calculations, but without any synergy, right? Without any benefit from this. Okay, so this is where then this big data regime comes in. And as I said, we need slightly different methods there. So I would say state of the art here in this field are graph neural networks as a kind of very general terms. There are lots of different types of graph neural networks, but what they have in common, and what the methods that we saw, Mace and Nequip and others, have in common, is that they still use this idea of local environments, and they still use the idea of symmetries and all of these things, because those are good, right? Those are things that help us. But there's a couple of enhancements that allow us to be more accurate and also to kind of treat these large data sets. And one of them is message passing. You may have heard about this. So the idea is now we have a local environment descriptor, but then we have a mechanism by which the local environment can talk to the local environment of the neighbors, right? And this does two things. On one hand, it sort of enhances the receptive field of our model, right? Because now there is information about my neighborhood within my cutoff, say 5 angstroms, but there's also information about the neighbor of my neighbor, right? This is more indirect information, but it is still there, right? So effectively, my model knows more than it knew before. But also, this increases the body order of the representation, which is a very important feature, actually. I think it's actually more important than increasing the range, but that's a different story. A very important point here is that all of these models use element embeddings. And this means that we are no longer treating the chemical elements as kind of discrete, independent species, but we are kind of embedding them in a continuous space, and we are learning the relationships between the elements. And this is key, and I mean, this also matches chemical intuition in many ways, right? So as a chemist, I know that, for example, chlorine and fluorine will have a certain analogy in the way they bond and so on, right? I will know that carbon and silicon have that kind of analogy. And the more using element embeddings is sort of a data-driven way to enable the neural networks to also learn that kind of information, those kinds of correlations. And that's important for a reason that I will say in a bit. Also, they tend to use directional information, right? So equivariant neural networks are all the rage here. So this means that we are not only using kind of invariant information about interatomic distances, but also kind of the direction in which atoms are lying, which gives us kind of higher body order information, essentially angular and higher order information. And again, you end up with a kind of zoo of methods. Really, the pioneers here, I would say, were the Schnatt people. So this was Christoph Schitt, together with Alex Tachenko and Klaus-Robert Müller, who presented the Schnatt model in 2017. So that already had message passing and element embeddings. It was missing the directional information. That came a bit later, either in invariant networks with Stefan Günnemann and Johannes Gasteiger doing the DiamondNet and GemNet models, or here Simon Batzner and Boris Kosinski and Ilyich Bhatia, and Gabor Chani doing Nequip and Mace, respectively. And a lot of other people that I'm probably, it's really hard to keep track of all of these different models, but these are just some examples, just to say we have, I think, a certain convergence of the field towards this type of approach. Okay, so what does that get us, right? So this is, at first glance, it's definitely more complicated, right? It also means that it's more expensive, right? But it has advantages, and the first work that we did in this direction was in 2022, together with the group of Stefan Günnemann, who had developed the GemNet model. And what we were seeing at this time were that these models would kind of beat all of these benchmarks, right? In computer science, in AI research particularly, you have a lot of benchmark. It's very benchmark driven, right? Which means that there's some kind of data set online, for example, the QM9 set I just showed before, or the QM7X set I'm going to explain in a bit. And then there's a predefined train validation test split. And people build their new machine learning algorithms and then run them on these predefined train validation test splits. And if they're better by some fraction, then they have a table in their paper where their number is in bold, and then that's what they want. Right? And as a scientist, this makes me a bit uneasy because you see, okay, there's a lot of progress there. The RMSDs are going down. Everyone has their bold number in a table somewhere. But the question, of course, is, is that useful for me, right? So that's what we were kind of trying to explore here. And so we took this data set from the Tkachenko group. This is a chemical data set, like an organic chemistry data set. So it contains molecules. It's called QM7 because all of the molecules have up to 7 non-hydrogen atoms, right? So this really restricts the diversity of chemistry you can have, right? You can have like a benzene ring and one functional group, or you can have like a heptane or something like that. But by restricting the space, you can be very exhaustive. You can essentially enumerate all kinds of connectivities that are reasonable that you can have with up to 7 atoms and up to these 6 elements that are shown here. And then they did a lot of work to really explore that space, right? To really nail it down. So they did different stereoisomers, they did different conformers, and then for each conformer they did non-equilibrium structures by sort of doing normal mode displacements there. And then you end up with a big database, and it has, I think, something like 4 million single point DFT calculations, right? And this is nice because it allows you to really go from the low data to the large data limit. And so you can do these training curves, and then you get what I just mentioned, this test set performance, right? And you can see, Schnedt, as I mentioned, these are really the pioneers of these message passing networks. And then DimeNet and GemNet, these are 2 different types of networks from the Gunnemann group that incorporate more and more higher order information, essentially angles and dihedrals, to put it simply, so 3 and 4 body terms. And what you see is that, so these enhancements clearly make things better, right? So you get a bold number in your table. And GemNet here is the best. It's also the most complicated, most expensive model. One thing that I didn't necessarily expect, and I think that really also changed my view on this field a little bit, is that this is true not just for the big data limit, but it's also true for the small data limit. So even if I just take a 3,000 of these configurations to train, of course my error is bigger, but still GemNet is the best model. Yeah? And coming sort of from a traditional statistical perspective, my hunch would have been that there's some scaling of the complexity of the model and the optimal training set size, right? So this thing here, I think it has like 2 million fittable parameters. Yeah? And you're fitting 2 million parameters on 3,000 configurations, right? It's not quite true because you're fitting on forces, so you have a bit more information. But like in a traditional statistics setting, people would kind of send you home if you did this, right? This is not a good idea, right? But it does work. It does not overfit, right? Because this is the test set performance, and it works, right? I think deep learning people have an idea why that's the case, right? So this is not surprising for a computer scientist, but still, I had to kind of overcome this bias I personally had against using these overparameterized model in the small data regime. But they do perform quite well here. Okay, but that's sort of a side note, right? Because this is still the test set performance. So now I want to see how does that translate to kind of a real performance in application, right? So if I'm saying my force error, my root mean squared force error here for this small training set, this is the same as before. This is just the GemNet curve on the test set, removing the other 2. This is like 0.05 eV per angstrom root mean square accuracy on the forces. That's a pretty good accuracy, right? So this is, if I do a kind of a standard geometry optimization, that's my default relaxation criterion, right? So you would think that this model would be useful for me, right? If that error is actually representative of the out-of-sample error. And the way you can check this now is you just take a couple of molecules from this data set. So this is actually in domain. And we use these potentials to run MD. And not very long MD, but nanosecond long, right? So it's just to get some real non-equilibrium samples that the model itself generates. And then we do DFT single points to check whether it's accurate on these new samples that the model itself generated. And if you do this at 300 Kelvin, you can see that, okay, in the big data limit, there's an increase in the force error, but you would expect this a little bit, right? Because as you increase temperature, your forces overall are larger, right? So if you are kind of you say you're, I don't know, 5% accurate on your forces, then you would expect the absolute force error to increase as you increase temperature, right? And that indeed happens. Looking again in this limit, higher temperature means higher force error, but in a sort of predictable and consistent way. So I'm okay with this here. But what you see here is that for the small data limit, you don't have any robustness at all, right? Even though you're supposed to be, errors on the order of 0.05 eV per angstrom, you get errors that are like, 10 eV per angstrom, which is absolutely crazy. Yeah, this is completely unrealistic and useless. Okay, so what is happening here? So what happens here is that the models are not robust. So if I look at a particular MD trajectory here, this is, I think, at 600 Kelvin for this little molecule here, and I run it for a nanosecond, you can see that actually the energy error is quite low for most of it, but at some point it reaches a place on the potential energy surface that's never seen before, and it dissociates, it builds, it does these very strange things. You have a kind of bridging hydrogen atom here, very unrealistic, and suddenly the energy error goes up, right? So this is kind of what I was afraid of, that you have a tested error that tells you you're good, you're safe, but then you run a simulation and actually you observe much larger errors. But this is only really true in the small data limit, right? So the GEMNet model, if you show it enough data, it is quite robust, right? There's no telling what happens if I go to 5,000 Kelvin and if I do 10 nanoseconds, right? So at some point, probably it will break down. But doing these kinds of simulations at least gives us a sort of a idea of how robust it is, right? Also relatively speaking. And you can actually extrapolate remarkably well with these models. So this is the biggest model we had. And now we did a bunch of other molecules, right? And remember the QM7X has 7 heavy atoms. So it has basically a benzene with a methyl group or a OH group as the biggest molecule. But here you can do different things like benzene with 2 functional groups, fused ring systems. This is an amino acid. This is a tripeptide. And all of these have never been seen before. But both the energy prediction here for MD samples generated with this potential, validated with DFT, and also the force errors are remarkably small, right? So for this biggest molecule here, you see some systematic shift of the red dots, but overall really good, yeah. And what is also remarkable, so it is again not just the data that you need, right? It's not just the 3 million training configurations that help you here, but it's also the architecture, right? So having this GEMNet Q, our best, most complex model, taking into account 4-body interactions and whatnot, that's what makes it robust at this training set size. If we have a Schnet model, we train it on the same data. It's not just worse in terms of the RMSD, but it's also completely lacks robustness, right? So you see here, there's very little correlation between the DFT and the machine learning forces and energies in this case. And so that was our first impression of, okay, extrapolation and actually works if you have a powerful modern GNN architecture and if you have a lot of data. But nonetheless, I was still, I'm not very good at predicting the future, obviously. I was still surprised when Gabor came around with this Maze MP0 model. Yeah. So this has now a coverage of 89 elements. This is one of these foundation models that we've heard about several times now already. It's trained on data from the materials project, so specifically the MP Tredge data set, which takes 150,000 different crystals, right? So not even 150,000 different materials, and it essentially uses relaxation trajectories. So for each of these crystals, you get about 10 single points that are actually also highly correlated. So this is, I would say, the opposite of like a well-constructed data set for machine learning. But it is what was there, and so people used it. And to me, it's not obvious at all that this would work, right? And we just had this discussion, right? So just the back of the envelope calculation, if you have 89 elements and you want all ternary combinations of these elements, you need about 600,000 different materials. But we just have 150,000, right? So I was really surprised. But as other people were not so surprised. And the argument here is that this embedding and the fact that the machine learning potential is kind of learning a continuum of elemental species and atomic environments, and that these things are quite systematic in nature, allows it to have this kind of extrapolability, right? So that's one part of the story, and that's already quite impressive in my view. But then the other thing, and where we were also like now slightly involved here, is that this was not just good for the crystals and the types of crystals it was trained on, but it was remarkably stable in all kinds of settings, right? So one thing, for example, oh yeah, I should mention here, so this was 2023, I think, like a day before Christmas or something, where this went up on archive. Since then, of course, other models have come out, especially also other much bigger data sets, but I'm going to show just sort of the original MP-Trudge-based model. Yeah, but it doesn't really matter, right? So you can do even better, but I think this is already quite impressive in terms of this robustment. So for example, Martin in my group looked at solvent demixing. So this is not something where you would expect this to work at all, right? There's no liquid data at all in the materials project. There's a little bit of ice, water, and there's hardly any organic molecules because it's an inorganic crystal database, right? But nonetheless, you can put here water and benzene. You can run an MD simulation, and what you observe is that, you know, if you run this for a while, the benzene and water start to separate, right? There's a lot of things that are not good about the simulation, right? So for example, diffusion constants we've seen are not good. Yeah, so let's accelerate this a bit. So you see the separation, and you don't, it's not just trivial that it separates everything, right? So for example, water benzene, it will separate, water heptane, it will separate, water ethanol, at least on this time scale, it doesn't separate, right? I was surprised by this. I think this is a remarkable example, right? And even just that you can run these several nanosecond simulations of a liquid and it doesn't explode without any retraining, fine-tuning, I was quite impressed by this. Since then, Niels in my group has also worked a lot on vibrational properties. So we've looked at IR spectra. This was driven by Philipp Pracht. And we contributed basically some dipole models for this. You can predict with an organic foundation model IR spectra of diverse molecules with quite impressive accuracy, where essentially the deviation to the kind of favorite DFT function of the Grimmel group for this purpose, which is B3-lib3C, and the Mace foundation model. So the deviation between foundation model and functional is about as large as between the functional and experiment, right? So this is really useful. You can really use this from out of the box for predicting IR spectra of molecules in the gas phase. Similar here, porous materials, those are not part of MP-Trudge, right? They are kind of on purpose left as a validation set. So these are mainly MOFs and some COFs and some zeolites. And we calculated here from a database from Baron Smith's group the heat capacities. These are important for carbon capture applications. They work quite robustly. Yeah. I think, wait, I'm much too slow, so I'm going to skip some stuff. We've done materials discovery things, right? So you can do this kind of atom substitution. That also works quite well. Yeah, I was very slow at the beginning, so unfortunately, yeah, I'm going to skip this. But I do want to get to this point just to kind of follow up on where Alex left off, right? So how useful is this? And you see here DeepMind, right? So they put out a press release with this Nature paper saying millions of new materials discovered with deep learning, right? That's the headline. And then they say, okay, it's 2.2 million new crystals, and then there's these 380,000 that are stable, yeah, according to the kind of convex hull criterion. And then, of course, there was this collaborative study that went along with it, where they actually also went out to synthesize some of these materials from the materials project, actually. And this caused a big uproar, right? I particularly like this headline here, where it says "Robot Chemist Sparks Row," because it's a very cyberpunk kind of headline. But yeah, the reason for this was that, of course, when we do this kind of materials discovery and we predict perfect crystals, we are missing the disorder, right? We are not taking into account the presence of disorder. And so what we went out to do, well, if you look at the ICSD, a lot of materials are disordered. These were purposefully left out of the materials project because they are hard to treat, of course, right? And in particular, if you look at substitutional disorder here, this is actually a sizable chunk of the inorganic crystal structure database that has this disorder. This follows chemical trends. For time reasons, I cannot go into it. But it turns out you can actually make a composition-based predictor for this with a fair accuracy of about 90%. You can predict whether a certain composition is likely to display substitutional disorder. And now what you can do is you can take, of course, the ICSD. It has 35% of disorder, curated here because we remove things that have positional disorder. There's a kind of a different bucket. And if you look into the latent space of our neural network that predicts this disorder, and we put it into a two-dimensional projection, you can sort of see that it splits up into a disordered fraction and an ordered fraction, with the ordered fraction being the majority. And now we can look at the materials project, removing the ICSD crystals, so sort of the computational part of the materials project. You can see it follows a sort of similar distribution, also similar amount of disorder that we predict. And then you look at genome, and it has a very strong peak of the disordered part and much fewer ordered materials, according to our descriptor, right? And I think this really shows that if you are going for novel materials, you're going to end up with a bias towards disordered materials, simply because the known materials, especially in the materials project, are by definition ordered, right? So those are the ordered subset of the ICSD. And the reason you have a lot of these funky compositions, I think, in the genome data set is because they were avoiding already known compositions, right? But then you need to kind of also rethink whether the framework you're working in, which is ordered crystals, is a good framework for predicting materials. Anyways, okay, so I think I'm out of time, right? Okay, so just the last thing here. One thing that is, of course, missing from this whole framework is long-range interactions, which can also be important, especially at interfaces, especially for ionic materials, which you all care about. So this is a picture from Jörg Behler. It's a bit hard to see here, but if you look at this zinc oxide slab that is sort of metal terminated here and oxygen terminated here, and you add hydrogens, so you basically hydroxylate it at the bottom of the slab, then this is going to change the charge here on top of the slab. Yeah? And this kind of thing is really difficult for our kind of semi-local machine learning potentials to treat, because it changes something here that depends on something down here, right? And if this is not in the local environment of this, then there's no way for me to predict this. Yeah? And this is a tricky question. And of course, you can potentially deal with it by predicting the density directly, but that still doesn't get you this non-local information, right? Because if I predict the local density based on the environment, and it depends on something that happens elsewhere in my slab or in my system, I'm still not going to be able to treat it. And so the kinds of models that I think have emerged as so far the most promising contenders are charge equilibration-based models. So this is actually very related to what Benjamin was showing yesterday. In the chemistry languages, these are QEQ models, charge equilibration models. And you can sort of enhance these with machine learning by making their parameters machine learnable. And so we did this also. This is work by Martin Vondrak in my group. For time reasons, I'm going to skip it, but I just want to give you the punchline here, which is, so you can do this. You can use this, for example, to predict charge distributions of defects in solids fairly reliably. But they have some fundamental problems also. And this is shown here. So our most recent work on this, we looked at whether we can train models like this with applied fields. And the problem is that the field response of the QEQ-based models is wrong. So if you have DFT and you look at the energy versus the applied field, this is a water cluster, by the way, you see a more or less linear response, and the QEQ model has a more quadratic response. And this leads to qualitative failures here, because if I look at the DFT charges with an applied field, so this is the difference between having a field and not having it, and the QEQ, you can see that QEQ really polarizes the whole water cluster. So you have charge transfer from this molecule to this one down here. Whereas in DFT, what happens is that each individual molecule is polarized, but you don't have this long-range transfer. And this is a really big problem, and this is my last thing to show. This is just a nice movie. Also, like Esther, you have water doing strange things. So this is a water droplet, and when we apply a field in a QEQ model, super unphysical things happen. So we have two repulsive walls here, right, that avoid things from falling apart. But essentially what happens is, because the charge transfer between the molecules is allowed, there's a variational collapse where a part of the molecules get negatively charged, a part get positively charged, and they just fall apart. And that's a big problem that we really need to solve to make some headway here. Okay, anyways, my conclusions, but yeah, thanks for your patience.
Thank you.